Picture the solar system. Odds are your brain immediately goes to that classic science fair project we all had to build in the 4th grade. You know the one. Painted styrofoam balls, held perfectly in place by rigid wires. Those wires lock everything into predictable lanes, leading us to assume this is how planets naturally behave. We look at the big gas giants circling on the outside and the rocky planets near the sun, assuming this arrangement is a permanent rule of physics. Look closer at the history of our system, and that tidy clockwork vanishes. Our current arrangement is the wreckage left behind after a violent, chaotic cosmic crime scene. For centuries, we assumed our neighborhood was the standard template for the universe. Then came 1995, when astronomers peered through telescopes and confirmed the first exoplanets orbiting sun-like stars. They expected to find clones of our own system. They found chaos. Massive gas giants, worlds the size of Jupiter, orbit closer to their stars than Mercury is to our sun. These behemoths barrel inward on wild elliptical tracks, scattering smaller planets like billiard balls. These discoveries forced a complete rewrite of the rules. Planetary systems aren't collections of fixed tracks. They are dynamic arenas where worlds drift, migrate, and swap positions over millions of years. If the rest of the universe behaves like a chaotic billiards table, our own solar system must have experienced its own era of severe planetary migration. We just have to retro-engineer the evidence. 4.5 billion years ago, our solar system was a massive, cold cloud of drifting gas and dust. It would have stayed that way forever, except a massive star detonated nearby. That supernova sent a shockwave cascading through space, triggering our cloud to compress, spin, and collapse. In the center, gravity squeezed material together until it formed the protosun. But this young star was temperamental. It entered a volatile adolescent phase called the T-Tauri stage, blasting radiation and powerful solar winds outward. This created a 10 million year countdown, as the star actively blew its own planet-building materials out into deep space. The intense heat from the young sun created a boundary about 5 times the distance from the Earth to the sun, a zone astronomers call the frost line. Inside this line, the sun's heat vaporized water and other ices. The only materials capable of clumping together as solids were rare trace elements, silicates, and iron. Building a planet here was like trying to build a castle with only a few handfuls of sand. Outside the line, it was cold enough for water and methane to freeze. Ice is abundant in the universe. Out here, planetary cores could grow fast and massive, so massive that their gravity pulled in hydrogen from the nebula before the solar winds blew it all away. This strict temperature gradient sorted the planets at birth. Those forming close to the fire became tiny rocks, while those in the cold grew into kings. Jupiter was the first to take advantage of that deep freeze. Sitting in the sweet spot just past the frost line, it gorged itself on ice and gas, ballooning to 320 times the mass of Earth. It very quickly became the dominant gravitational force in the entire system. As Jupiter plowed through the thick soup of remaining nebula gas, the friction created intense drag. Constantly losing momentum, this massive gravity well began to spiral inward, directly toward the sun. This inward migration acted like a wrecking ball. Jupiter plowed directly through the inner solar system, sweeping away the dust and gas that Mars needed to grow. Jupiter would have eventually fallen completely into the sun if not for Saturn. Saturn formed slightly later and migrated inward as well. As it caught up, the two giants began to pull on each other, locking into a gravitational resonance that stabilized their orbits and reversed their course. By the time Jupiter retreated, it had swept the inner orbital lanes nearly clean. Mars was left to form in a depleted zone, with almost no raw materials to pull from, leaving it as a stunted fraction of its neighbors. As Jupiter and Saturn retreated, they eventually drifted into a new resonance. For every orbit Saturn completed, Jupiter completed exactly 2. Every time they lined up, they gave each other a massive gravitational shove, pumping huge amounts of orbital energy into the system. The smaller ice giants paid the price for this instability. The resulting gravitational chaos acted like a giant slingshot, hurling Uranus and Neptune violently outward into the darkness. When Neptune was evicted, it crashed directly into the ancient Kuiper Belt, a ring of trillions of icy comets. The collisions scattered this debris everywhere. Millions of icy rocks were thrown inward towards the sun, mercilessly pummeling the rocky inner planets in an event called the Late Heavy Bombardment. Earth should have been a dry, hot rock, but those violent impacts were a cosmic special delivery. The comets that smashed into our planet melted over millions of years, filling the basins that became our oceans. Once the bombardment stopped and the crusts cooled, the inner solar system held a rare sight. 4 billion years ago, 3 distinct blue ocean worlds orbited our sun simultaneously. But Mars was a victim of Jupiter's hunger. Because it was so small, its internal core cooled down and solidified rapidly. The planetary magnetic shield switched off. Without that shield, the constant stream of the solar wind physically stripped away the Martian atmosphere, letting its water evaporate into the freezing vacuum of space. Venus faced the opposite problem. It had shallow oceans for nearly 2 billion years, but as our aging sun slowly grew hotter, Venus crossed a critical tipping point. The rising temperatures evaporated its oceans, filling the atmosphere with steam that trapped more heat, creating a runaway greenhouse effect that proceeded to boil the planet alive. Mercury never even had a chance. The leading theory suggests it was once a much larger planet until a chaotic collision with another world literally ripped it apart, blasting its outer rocky mantle into space and leaving behind nothing but a dense, scorched iron core. Earth's habitability is a fragile achievement. We are simply the sole survivor of a cosmic elimination game, massive enough to keep our core hot and our shield up, and distant enough from the fire to keep our oceans liquid. We look up at the night sky and feel a sense of permanence, but the quiet, orderly system we see today is merely a temporary pause in a violent, ongoing timeline. The sun is still evolving. Driven by the constant nuclear fusion in its core, it is slowly turning up the thermostat. It is 10% brighter today than when the dinosaurs lived. As the sun continues to brighten over the next billion years, Earth will eventually be pushed out of the habitable zone. Our oceans will boil away, and we will share the exact same fate as Venus. We happen to exist right now, at the exact right moment to witness a fleeting window of cosmic stability. Planetary balance is incredibly fragile, and our blue planet is a temporary oasis.